Section 3.2, Rates of Change. In this section, we will calculate the average and instantaneous rate of change, and we will also solve application problems involving those including motion and business application involving marginal cost, revenue, and profit. Let's begin by talking about rates of change. Some of these terms that we're going to talk about are things that we already discussed in previous videos, so we're just going to recall that the amount of change of a function f is the change in the output values over the interval that you're talking about. So if you have an interval going from a to a plus h and you're asking for the amount of change, that just means you want to do the y2 minus the y1, meaning f of the second coordinate minus f of the first coordinate in your interval. Now, the average rate of change is something that we've also discussed before. This is just the f of a plus h minus f of a divided by h. And remember, we put a limit in front of it, and we put a limit in front of it, we get the derivative. By itself, this is known as the difference quotient, but with the limit, it becomes the derivative. And finally, the instantaneous rate of change. So if I ask you for the function's instantaneous rate of change at some point called a, so a is just a random real number, all I'm doing is basically asking you for the derivative evaluated at that point. And remember, this means that we're looking for the slope of the tangent line at that location where x is equal to the number a. So if you hear the words find the rate of change or find the instantaneous rate of change, that means they just want you to find the derivative and then plug in some random number in it. So let's talk about example number 1, and we'll see some of these terms being used here. So we're told in example number 1 that the temperature T, capital T, of a person during an illness is given by the function capital T of the small t, which is equal to negative 0.1 t squared plus 1.3 t plus 98.6, where capital T is the temperature in degrees Fahrenheit and small t is the time in days. So this function basically tells me the temperature of the person during the illness. The input of this function is the small t, and there's a difference between small t and large T or capital T in this problem. Small t represents the time in days that the person has been sick, and capital T is the temperature of that person after that many small t days. So in part 1 of the problem, it says find the initial temperature, meaning the temperature at time t equal to 0 days, and the temperature at t equal to 2 days. So we're basically finding two different temperatures. And then they want me to find the change in temperature over the 2-day period. So to find out what the temperature is at t equal to 0 days, so when the person was admitted or when the sickness started, all I have to do is put the 0 into the function that's given to me. So by direct substitution, I get negative 0.1, and I'm supposed to square the 0, and then multiply 1.3 by 0, and then finally add 98.6. So basically, I'm given t equal to 0. I plug it into the function that's given everywhere I see the small t. And obviously, this is going to be 98.6. And the degree here is in Fahrenheit, so we can add the unit degree F if we want to the answer. So this is the temperature of the person at the initial start of the illness. And now after 2 days have passed, if we want to know what the temperature of the person is, we just need to put 2 into that same function. Again, everywhere we see a small t. So I get negative 0.1 times 2 squared plus 1.3 times 2, and then finally plus 98.6. And so again, we're replacing the small t with 2 because that's what the question asked us to do. And when we plug this in, we can use our calculator, obviously, to get the answer here. The temperature turns out to be about 100.8. And again, the degrees in Fahrenheit, so degree Fahrenheit at the end. And that's the unit. So this gives me the solution to basically the first two parts of the problem when it's asking for the initial temperature and the temperature at t equal to 2 days. Now, the second part of the question said, what is the change in temperature over the 2-day period? So what do they want me to do here? The change in temperature is going to be given by the t of the second point minus capital T of the first point. In this case, there are 2 and 0. So all I have to do really is subtract 100.8 minus 98.6. That's the change in temperature over the 2-day period. And we can see that this is about 2.2. Okay, so that's the end of part 1, and I'm just going to color this so you know which answer corresponds to which part of the problem. Okay, so next in part 2, it says find the average rate of change of the temperature over the first 2 days. Well, the average rate of change is basically that difference quotient that we're talking about. Average rate of change in this problem is going to be, in this case, I'm going to do T2 minus T of 0 divided by basically 2 minus 0, which is the same thing as 2. So in this particular example, if you want to basically go back and trace what's A, what's H, and in this particular example, the small a would be the starting point and H would be basically the 2 value. It's not required to do this, but that's what I wanted to write here so that you can kind of relate the formula to what you see up here in the small paragraph that we were given previously. So in my case, I will have T2 and minus T0. We've already calculated that amount. That's basically 2.2. And I'm supposed to divide it by 2, and the answer turns out to be 1.1. And if I want the unit here, then I will have to have degrees Fahrenheit, because it's the numerator, it's measured in Fahrenheit, and the denominator is measured in days. So that is the answer. 1.1 degrees Fahrenheit per day or per days. If you want, we can use singular here. Okay, so next is asking us to find the function representing the instantaneous rate of change of the temperature at any time small t. So notice how they're asking for the function that represents the instantaneous rate of change. So whenever I hear the instantaneous rate of change, I'm thinking derivative. So they want basically the function that represents the derivative. So remember, we were given capital T of small t. The original function that we were given was negative 0.1 t squared plus 1.3t plus 98.6. So from this, they want me to create the function that gives the instantaneous rate of change. So in other terms, they just want the derivative. And so we can use our brand new rules, like the product rules, quotient rules, or the simple basic rules to find the derivative here. I think for this problem, it's enough to use the basic rules to find the derivative. So for negative 0.1 t squared, the negative 0.1 is not going to matter for a moment. And we just differentiate the t squared, which is going to give us 2t. Remember, there is a product between the constant and the variable, so we ignore the constant and we just differentiate the variable. So we bring the power down, then we subtract 1 from the power. Similarly, again, between the 1.3 and the t on the second term, there's multiplication. So again, the 1.3 goes for the right, and then we multiply by the derivative of t, which we said previously is just 1. And finally, the derivative of 98.6, that's going to be 0 because that is a constant all by itself. And whenever you have a constant by itself, the derivative is going to be 0. So in other terms, what I'm saying is that the t prime, meaning the function that gives me the instantaneous rate of change, which depends on little t, which is the number of days that have passed, is negative 0.2 t plus 1.3. So that is the final answer for that part. Okay, and finally for part 4, it says find the instantaneous rate of change of the temperature with respect to time at t equals to 2 days. So again, I'm supposed to plug some number into some function, and in this case, I'm hearing the word instantaneous rate of change. So that means they want to plug 2 into the derivative equation that we just created. So I'm going to put t apostrophe 2, meaning the instantaneous rate of change at day 2, is going to be negative 0.2 times the value 2 plus 1.3. So that 2 is in the problem, that's why I'm plugging it in. And this is going to be negative 0.4 plus 1.3, which adds up to 0.9 degrees Fahrenheit per day. So it seems that the temperature of the patient is increasing by 0.9 degrees Fahrenheit every day the illness stays. So everything so far has been sort of familiar, but now we're going to start a new topic, which is the motion applications. And so in this particular page, and in this particular section, and in this course, we're going to talk about motion, but we will only consider motion along a horizontal or vertical line. This is known as rectilinear motion. So in the few problems that you'll see in this course, you're going to see 3 different variables, s of t sometimes, v of t sometimes, and then a of t. So let's talk about what those symbols are and what they mean. So s of t represents the position of the object at any point in time called little t. And v of t represents the velocity of the object at any point in time t, whereas the small a of t represents the acceleration of the object at a point in time called t. Now, what's important for us in this section is to know how these three connect to one another. And the relationship is this: if you're given s of t, the position of the object, and you want to know the velocity of the object, all you have to do is take the derivative. So take the derivative of s, and you will get v of t. Now, if you have the velocity of the object, but you want to know the acceleration of the object, then again, what you would do to go from one to the other one is you would take the derivative. And that's what's being described in this paragraph below. So it's basically giving us the relationship between v and s, and also between a and v. So again, s is the position, and I'm not sure why they use the letter s in physics, but that's the way it works. And v stands for velocity, and finally a is the acceleration. So in this particular section, we're always going to be given s of t, and we want to find the other two variables or the other two functions. But in later sections in this course, we're going to be giving you the acceleration, and you're going to have to find v somehow, and then you're going to have to find s of t somehow, and that involves the opposite of differentiation, which we're going to call anti-differentiation. But for now, this is what we need to know. And also keep in mind that velocity could be positive or negative, but speed is not exactly the same as velocity. It's the absolute value of the velocity. So if I ask you, what's the speed of the object? You just take the velocity, you plug some number into the function, into the equation, and you get a number. It could be positive, it could be negative, because the object could be moving up or down or left or right, depending on your orientation. But the speed is just the absolute value of that value that you just calculated. And it's always going to be positive. Now, keep in mind that if the velocity is positive, that means your object is moving up or to the right, depending on your frame of reference. And if the velocity is negative, so if you calculate the velocity and it's negative, then the object is moving down or to the left, again, depending on what you decided your positive orientation is going to be. But speed is always positive because speed is the absolute value of the number. So let's take a look at an example. And example number 2 says, suppose that an object moves up and down on a vertical line, kind of like a yo-yo, basically, such that its position above the ground is given by the function s of t equal to t cubed minus 3t squared plus 20. And in this problem, we're assuming that the small t is a number between 0 and 4, possibly equaling to 0 or equal to 4. So basically, the experiment is going for about 4 seconds. So we're making this object move up and down along a vertical line, kind of like a yo-yo, for 4 seconds. And s is measured in centimeters. So that's just the unit of the distance. So in part 1 of this problem, it says find the position at t equal to 1 second. So remember, s of t is the position function, and we want to know the position of the object after 1 second, or at t equal to 1 second. So all I have to do really is plug 1 into the given equation. So it used to be t cubed minus 3t squared plus 20. So what I have to do is basically erase the t's and write in their place the value that's given to me in this problem, which in this case is just the value 1. And in this problem, I get 1 minus 3 plus 20. So, 21 minus 3, which is equal to 18 centimeters. And it's going to be basically above ground, let's say. So pretty straightforward. This is the position. So remember, the keyword here is position, and position is the s of t function. Now, for part 2 of the problem, it says find the velocity and speed at t equal to 1. So they want the velocity and the speed, and I'm not given in this paragraph anything about velocity or speed. They're just telling me the position. So what I have to do is start with the position function, and I'm going to write it down again one more time. This is t cubed minus 3t squared plus 20. And I have to say, or remind you, or recall, or whatever, however you want to say it, I have to remind you that the velocity is just the derivative of the position. So it either is written as s prime of t, s apostrophe of t, or you can write something like d over dt of s of t. This notation just means we want the derivative of the function s of t to get the velocity of the object. So in other terms, if I want the velocity of the object, what I have to do is I have to take the derivative with respect to the letter t, meaning the t is the variable that I'm differentiating with respect to, and the equation is t cubed minus 3t squared plus 20. And so in this particular problem, again, I could use the basic rules. Since I have pluses and minuses, I just differentiate term by term, each one of these three terms. And so the derivative of t cubed first will be 3t squared, 3t squared. Then the derivative of negative 3t squared will be negative 3, and then the derivative of t squared is going to be 2t. And finally, the derivative of 20 is going to be 0. And you know what? Let's not write it down. So ultimately, my velocity function or my velocity equation is 3t squared minus 6t. So this is an equation that tells me the velocity of the object at any point in time between 0 and 4 seconds, because the valid domain in this problem was 0 to 4. Now, we're interested in finding the velocity and speed, but only at the point t equal to 1. But in order to do that, we had to find the whole equation first. And so now we can finally say, well, the velocity at time 1, which is again the value that's in the problem, the velocity at time 1 is going to be 3, 1 squared minus 6 times 1, which is basically 3 minus 6, which is negative 3. So as you can see, the number could be positive or negative. In this case, it turned out to be a negative value. And this is velocity, and the units in this problem are centimeters per seconds. So that gives us the velocity. So I'm going to highlight it in blue so you can remember that this reminds us, or this is the answer to velocity. But the speed of the object is that number in absolute value. So it's the absolute value of negative 3, which is going to be 3, and again, centimeters per second. So what's the difference? The difference is that this number here tells me direction, so it's negative 3, so it's maybe going, up or down. In this case, because it's negative, I'm going to assume it's going down, whereas this is just the actual speed at that moment in time. Okay, so what I just said, I have to write here. So after 1 seconds, is the object moving up or down? So by noticing that there's a minus sign in front of my 3, I'm going to say that the object is going down. And we will have to calculate this value to be able to answer what's going on after 3 seconds. So first, at time t equal to 1 second, the object is moving down. And that's because the velocity is a negative amount. So I'm going to write smaller than 0. That means that the velocity is negative. Now that answers the first part of the problem. And for the second part of the problem, I need to know what's going on at 3 seconds. So let's see. At t equal to 3 seconds, I will need to find first the velocity of 3. So meaning I'm going to take the velocity equation, which was 3t squared minus 6 times 3, and I'll have to plug in it the value 3 for all the t's. And so this is going to be 3 times 9, which is 27, and then 6 times 3, which is 18. So the number here will be 9, and it's the velocity, and velocity is measured in centimeters per second. Remember, it's the distance unit on the numerator and the time unit on the denominator. And in this case, the problem told us that the distance was measured in centimeters, whereas time is measured in seconds. So that's why I'm always putting centimeters per second on my units. And that's the end of velocity at 3. And what I want to point out here is that the number that we got was a positive amount. So it's a positive 9. So that means the object is moving up. So at t equal to 3 seconds, the object is moving up. and that's because the velocity was greater than 0. By the way, if the velocity ever happens to be equal to 0, then we will say that the object is not moving at that moment. It's just kind of sitting still for a moment. Okay, we get to the last part of this problem, which asks us for the acceleration at time t equal to 3. So remember, the position function was given to us. It was t cubed minus 3t squared plus 20. We calculated the velocity by doing the derivative of the position function, and we got 3t squared minus 6t. So now we want to know the acceleration of the object. So to find the acceleration, we will have to do the derivative of velocity. So acceleration function, a of t, is the derivative of the velocity function, meaning I want the derivative with respect to t of the velocity equation. So whatever my velocity equation is, I'll just have to find its derivative. So meaning I want the derivative with respect to t of 3t squared minus 6t. And again, we can use the basic rules here. We don't need any fancy product rule or quotient rules to get the acceleration equation. So in this case, I'll just differentiate 3t squared. The 3 is hanging out. The t squared becomes 2t when you differentiate it. And then the derivative of 6t is going to be 6 times 1 because the derivative of t is equal to 1, and the 6 is being multiplied with the t. So the 6 goes for the ride, and ultimately this is going to be 6t minus 6. So that's the equation that describes the acceleration of the object, but we care about a specific moment in time when the time is equal to 3. So at time equal to 3, the acceleration of the object at 3 seconds, and we would write a of 3. That means we're going to plug 3 into the equation for acceleration. This is 6 times 3 minus 6, and 6 times 3 is 18. 18 minus 6 is going to be 12, and the unit for acceleration is always centimeters per second squared. So it's the unit for position on the numerator, and then the unit of time squared on the denominator. So in this case, the time is measured in seconds, so seconds squared, basically. So to summarize, if you're given the position function and you want to know the velocity function, to get the velocity, you would have to do the derivative of the position function. And if you want acceleration, then you'll have to do the derivative of the velocity equation. So in other terms, what this really says is that if you want the acceleration, you would have to do two derivatives of the position function. So you would have to do the derivative basically once to get the velocity and then once again to get acceleration. So that's the relationship that you need to kind of pay attention to and memorize and know for future exams and quizzes and problems that you'll do on the homework. So let's continue with example 3 that says, suppose that a ball is dropped from a height of 120 feet and its height above the ground in feet t seconds later is given by the equation s of t equal to negative 16t squared plus 120. So this is now the position function that tells me where the ball is after it's been dropped from 120 feet above ground. So t is in seconds, and the unit for distance is feet in this particular problem. Now, what they want from me in part 1 of this question is the instantaneous velocity at time t equal to 2. So instantaneous should always start reminding us from now on that they're talking about some kind of derivative. And what the derivative is in this case is the velocity equation. So they want basically the derivative of s of t. And not only that, but they want me to plug in 2 into the equation that I get. So I've got a couple of things to do. First, I'm going to write down the s of t equation, which is negative 16t squared plus 120. Then I'm going to write recall or remember that if I want velocity equation, then I'll have to just differentiate the s function, meaning take the derivative with respect to time of the s equation that you're given. So in this problem, the velocity is going to be equal to the derivative with respect to t of the equation negative 16t squared plus 120. And I'm just going to do a little bit of mental math to get the answer here. The derivative of negative 16t squared is going to be equal to negative 32t, and the derivative of 120 is just 0 because the 120 doesn't have any value t or any, let's say, variable t next to it. So this is the equation that tells me the velocity at any moment in time because it has the variable t in it, small t. But we want to know specifically at time 2 what's the speed or what's the velocity in this case. So at time 2, at t equal to 2, the velocity at 2 seconds is negative 32 times 2, which is negative 64, and the units are feet because that's the distance unit, per seconds because that's the unit of time. So negative 64 feet per second. So it seems that the object or the ball that we dropped is going down, which kind of makes sense. It's been dropped from 120 feet above ground. And so the negative tells me that the direction or the orientation of the ball is down. And so we can see from the graph that it's about, let's say, 55 feet above ground, right? Remember, this is the graph, and at time 0, we know that the ball was 120 feet high. This is the position graph. And so after 2 seconds, I can guess from the graph that the ball is about 55 feet above ground, maybe, and it's going at the speed of at the speed of 64 feet per second. Velocity is negative 64 feet per second, but the speed is 64. So in other terms, if I want to know the slope of the tangent line at that location, that tangent line has slope which is negative 64. So negative tells me the line is pointing down, and at this location, the height of the ball is around, let's say, 55 feet. So now they want to know the impact velocity, meaning the velocity when the ball hits the ground. So at some point in time, the ball is going to hit the ground. We don't know. It seems from this picture that the number should be between 2 and 3 seconds. So maybe it's 2.5, maybe it's 2.8. We don't know. But we need to know the time so that we can tell them the velocity or the speed at that moment in time. So they want two things from us. They want the impact velocity and also the speed. So once I get velocity, all I have to do is just take the absolute value of it to get the speed. So let's focus on finding the velocity at the impact time. Now, in order to find the impact time, I need to use the original S equation. So remember, S of t is the function which was negative 16 t squared plus 120. I need to use this equation to figure out what time it will be when the ball reaches the ground. So at ground level, the position of the ball is going to be equal to 0 because my ball is basically on the ground now. So I know that S of t will be 0 there. So in other terms, what I have to do is use the 0 and replace S of t with 0, and I will get the equation 0 equal to negative 16t squared plus 120. When I solve this equation, there's only one letter in there, or one variable. It's the t, which will give me the time it will get to the ground. So I'll be able to figure out what time my ball is hitting the ground, and once I have the time that the ball reaches the ground, I'll use that t and go back to the velocity equation, plug it in, and I'll be able to determine the velocity and therefore the speed. So it's kind of a double whammy here. We have to do two things to get to the solution that we want. We first have to solve an equation where we replace S of t with 0. And again, that's because the ball is now on the ground. When it hits the ground, it's on the ground. And so that's why replacing S of t with 0. The distance traveled is 0. And so how do I solve this equation? One way to do it is to move the 16t squared from the right side to the left side. And when I move it around, it becomes positive. It loses the minus. Then I can divide both sides by 16. So 120 divided by 16. That way I can isolate the t. And so t squared will be 7.5. 120 divided by 16 is 7.5. But since t squared is 7.5, the t itself is either plus or minus the square root of 7.5, and remember this is in seconds. Now remember, there are two options here because there are two numbers that we square to get 7.5. It's either the positive version or the negative version. Both of them will square to become 7.5 later on. However, this is an actual physics problem with ball and time and motion and so on. So time cannot be negative. So we have to pick the choice that is positive. So we have to pick 7.5 instead of both answers, which are negative and positive. Time can't be negative, it's got to be positive. So I have to choose this version, 7.5 inside the square root, and the unit again is in seconds because this is, after all, time. So roughly speaking, this is square root of 7.5, and let's put it in our calculator and see what this value represents. So calculating the square root of 7.5, I can see that the number is roughly 2.74. And that's good news because I expected the number to be between 2 and 3. So 2.74 seems like the right answer. So now that we have the time, awesome, we can finally answer the question, which is what's the impact velocity? So I'll continue over here to write impact velocity. And the impact velocity is basically the velocity at the square root of 7.5, which we calculate to be roughly 2.74. And so again, using my velocity equation, which was negative 32t, I'll have to replace t with the square root of 7.5. And that will be it. So the velocity at this impact moment is going to be, roughly speaking, let's put it in our calculator and see what the value is. So negative 32 times the square root of 7.5 is about negative 87 point, let's say 64, since we're rounding to two decimal places. They didn't really say which decimal place they want me to round to, so I'm just going to round to two decimal places by default. So let's say negative 87.64, and the units are going to be feet because that's what we were told per second. So that is the velocity at the impact moment. So after 2.74 seconds, the ball hits the ground and it's going at negative 87.64, which tells me that the ball was going down at this moment. And therefore, the speed is the absolute value of the velocity at this moment. So the absolute value of negative 87.64 is going to be 87.64. And again, the unit is basically the same, feet per second. Okay, so that is the application that has to do with motion. And next, what we'll have to do is look at business applications. So in this course, again, you are going to see these words multiple times. The words are going to be cost, revenue, and profit. These variables are going to be showing up over and over in our course. But now we have new terms to worry about, which are the marginal cost, marginal revenue, and marginal profit. And what these are just the derivatives of the cost, revenue, and profit, respectively. So marginal cost is the derivative of cost. Marginal revenue is the derivative of the revenue equation. And marginal profit is the derivative of the profit equation. And these are used to approximate the change in cost or revenue or profit when we produce or sell one additional unit or item. So for example, if I ask you to calculate in a certain problem the marginal cost of 100, that means I'm asking you to find the derivative of the cost function, then plug in 100 into it. And what that number is, it's an approximation for the cost of making the 101st item. So in example 4, we are told that the price in dollars and the demand X for a certain Bluetooth speaker is given by the price demand function P of x, which is 143 minus 0.03x. So in this problem, x represents the demand of the speaker, the Bluetooth speaker, and P is the price that you should sell it at. So part one, it's asking for the revenue function R of x. And this is something I have to tell you. The hint here is that the revenue function is just the P of x function. So this guy right here multiplied by x. This is not told, this is not written anywhere on the page, but think of it like a formula basically. So this is an important one to also remember. So if I want the revenue equation, but I'm only given the price demand function, to get the revenue, I have to multiply x by the price demand function. So multiply all this by x. So in other terms, the revenue equation in this problem is going to be 143 minus 0.03x, all multiplied again by another x. So this initial part represents the price demand equation, and this is just the number of items we're trying to basically sell. So in other terms, what we're saying is that the revenue equation in this problem is 143x minus 0.03. X times x will become x squared. So that is the revenue equation, which is great. And for part two, it says find the marginal revenue. So remember, marginal revenue is just a derivative of the revenue equation. So I'm going to write MR for marginal revenue. It's the derivative of the revenue equation. And so what's the derivative of 143? X, it's going to be 143. And what about the derivative of negative 0.03 x squared? Well, that's going to be 0.06, just x. So that is the marginal revenue equation. Simple, it's just the derivative of revenue. So once you have the revenue equation, you just differentiate it. So now the question for part three is to find the marginal revenue of 1,000 and then 4,000s, and then we have to answer what do these values tell us. So again, we have the marginal revenue equation. We've calculated it. So we have the equation. All we have to do now is put 1,000 in it and then put 4,000 in it again. So our prime of 1,000, the marginal revenue at 1,000, is going to be 143 minus 0.06 times the x. But in this problem, we're choosing x to be 1,000 because that's what they gave me in the problem. So 143 minus 0.06 times 1,000, you can use your calculator to get 83 as the answer. So this is 83. And so what does this number mean? This number says that the revenue from selling the 1,001st speaker, the revenue from selling that is going to be $83. Now, our prime of 4,000 is basically the same. I'm just going to take my previous equation that I just found and plug the 4,000 into that equation also. So 4,000, because that's what the question told me to do. And if I do 143 minus 0.06 times 4,000, the answer will be 23. So what does this mean? This means that the revenue from selling the 4,001st item, the revenue from selling that speaker is going to be 23, and the unit is dollars. So that's the revenue from selling the 4,001 speaker, whereas the first number was the revenue from selling the 1,001st speaker. So you might be wondering, like, how does this make sense? And maybe to sell 4,001 speakers, maybe I have to put some ads on TV or radio or whatever, or the internet, and I have to advertise, maybe give some discounts to customers or whatever the case may be, but I'm getting less revenue from selling that additional one more speaker once I've reached 4,000 than I did when I had sold 1,000 speakers and then I sold an extra one. The revenue there was better for I'm selling the 1,001st speaker. maybe I had to advertise less, or the demand was really high at that point, so everybody was dying to get one of those speakers, but not so much when I've sold 4,000 of them already. In any case, let's continue to problem or the part 4 of this problem. It says if the cost function is given by c of x equal to 75,000 plus 65x, find the profit function. So remember, they're giving me the cost, but they're asking for profit. So remember, the profit function is called p of x. And how do you get the profit? You will subtract r of x minus c of x. So you subtract revenue minus the cost. And in this problem, revenue, we determined that it was 143x above minus 0.03x squared. That was the revenue. So I'll highlight it in yellow so you can trace it. This is that part. The formula tells me to put a minus next, so I'm going to put a minus in the middle. And then I'm supposed to subtract the cost equation. So the cost, we're told, is 75,000 plus 65x. So that represents the cost, and in this problem, cost is given to us up above in the problem. So we don't have to do any derivatives here, we just have to subtract some terms, but be careful when you're subtracting. The minus on this middle part has to distribute to the two terms that follow, so let me do that first. 143x minus 0.03 x squared minus 75,000 and then minus 65x. So the last thing I want to do here before I move on to the next part of the problem is to just combine like terms and write the answer in standard form just because it looks prettier that way. So I'm looking at any terms that have x squareds first. There's only one of them, so I'll put that first in front. And so I'm kind of done with that middle part. And next I'll use the x terms. So I have 143x and then 65x. So, you can use your calculator to do this. 143 minus 65 is going to be 78x. And so I'm kind of done with those two parts now. So I finished basically looking at all the x's and all the x squareds. The only thing I have left is just the good old 75,000 with the negative in front of it. So I'll stick that at the end. And now we are done writing the problem or writing the profit equation in the standard form. Okay, so finally for part 5, we're asked to find the marginal profit at 1,000 and at 2,000. So the marginal profit, that's usually called MP. It's basically the profit equation, but the derivative. So find the derivative of the profit equation. So we want the derivative with respect to x of negative 0.03 x squared plus 78x minus 75,000. So that's the profit that we created before. We just need to differentiate it. And we don't need any fancy rules here. All we have to do is use the basic differentiation rules. So negative 0.3 is being multiplied with the x squared, so we just differentiate x squared, which gives us 2x. But we got to multiply with the negative 0.03. That's going to be negative 0.06x. Next, we have the 78 with the x next to it. So the 78 is just going to hang out, and we differentiate x, but the derivative of x is 1. And 78 times 1 is just 78, so I'm not going to write the 1. Finally, minus the derivative of 75,000, the derivative of that is going to be 0, and we're not going to bother writing it down. So this is the marginal profit equation. It's a simple little equation, negative 0.06x plus 78. But now they want me to find p prime of 1,000 and then 2,000. So that's not too difficult. We'll just plug in 1,000 into the equation that we just created, 0.06 times 1,000 plus 78. And that will be approximately 18. And that's done. And also, since they asked for the profit, marginal profit at 2,000, I'm going to plug in 2,000 into that same equation. So negative 0.06 times 2,000 and plus 78. And the p prime of 2,000 will be, okay, sorry about that, will be equal to negative 42. So we got the two answers, and we are completely done with the problem. So remember, the 18 over here represents the profit from selling the 1001st speaker, whereas the negative 42 represents the profit from selling the 2001st speaker. So my profit is now negative, by the way, so maybe we should stop selling these speakers at some point in time between 1000 and 2000. We don't know what that number is. We didn't take a moment to find it, but that's what these numbers are. So the profit from selling the 1001st speaker is $18, whereas the profit from selling the 2001st speaker is negative 42. And because the number there is negative, we're losing $42 when we're selling that 2001st speaker. So maybe we should stop selling the speaker at that point in time.